Okay, any questions?
A question like a little earlier, like I'm having difficulty with like my k square root x is isomorphic to kx, those kind of things, like when doing
Oh,
bidirectional, because
that is, there is no geometry in that. That is just an algebraic fact.
but that is an algebraic extension of kx, so that k square root x is an algebraic degree 2 extension of kx, then how can they be isomorphic? So you need to learn into it. Even in the midsem there was a question like k square root x plus 1, there was those kind of extensions, those are degree 2 extensions over kx.
It is, I mean, so in some sense, those are infinite things. So infinite things, they could be in bijection, even if one is a subset of the other. So you have already seen this with even numbers and integers.
I understand that, but
So
like,
integers are as many as there are even numbers. It's the same thing.
but t square minus x, that polynomial, one will be irreducible and other will be reducible, right? If I take the
No.
kx of the polynomial ring.
Uh, so you have kx
Of t,
and square root x, and the map which we define is
x for square root x goes to like x, I think. X goes to square root x, something like that.
yeah, that's the only thing you can do. So you can map x to square root x,
Okay,
and then this is a map only on defined only on one element, but you can generalize it to, I mean, you can extend this to all the elements, right? Because now all fractions like this become this. So you can see that this is a phi is a field homomorphism. It's a field homomorphism, and you can see that the it's not the zero map, of course. Now you know that field homomorphisms are isomorphisms, are embeddings, right?
because I'm saying that this polynomial like t square minus x, the first field is irreducible, but in the second field it is reducible.
T square minus x, so you are saying that why don't you take this, the polynomial ring. So where is t square minus x mapping to? So this is actually mapping to this. That is the mistake. So irreducible will go to irreducible. So this x that you are thinking, there is actually no common x. This is x and this is some y. It has, there is, I mean, sure, they have a common word which is kx, but I don't need to think about that. I can just think of this as ky. And what we are showing here is just that kx and ky are isomorphic. Now y you can take to be any function in x. Same proof will work. As long as you don't take y to be, I mean, y has to be transcendental. It should not be some algebra, it should not be in k bar. So this proof is actually true for any y not in k bar. That is the thing. It's yeah, but definitely it's confusing. That's why we saw this example geometrically. Any other questions? Okay. Hmm. So what we have been doing 2 weeks ago is we started divisors of a curve, which for us is now just a function field big K, transcendence degree 1. So the free, so divisors of C is just formal combinations, integral combinations of points, where point should always be thought of as a prime ideal. Right, so in the polynomial ring, it's just a prime ideal that we are looking at. So this prime ideal actually may not represent just a single point. I mean, it could be a single point in the algebraic closure, or it could be many points. When it's many points, then we have seen examples where it's basically the conjugates that are clustered in a cloud. So there is this concept of degree of a point. So it's not really a point P, but it's just it's a cloud of points. And then we define degree and div 0 support every point P actually defines a valuation, which is if you remember the theory that we developed before, you basically have to look at the germs and the maximal ideal, and since the maximal ideal will be principal, its generator gives you the valuation. That's by uniformizer. Also, small k in this divisor theory, small k may not be fp bar, it can be any finite field as well. Fine, then we saw that for a rational function, I mean we saw this example basically, this x2 square x0 minus x1 cubed example was instructive. So function here is x1 by x2, and we saw all the zeros and poles, right? So zeros are p1 and p2 and poles are p3 and p4. So the principal divisor of this x1 by x2 is p1 plus p2 minus p3 minus p4. That is it's an important example to remember, because here the degree comes out to be 0. We'll show this actually now for all rational functions. And so these divisors are called principal divisors, div A, which correspond to rational function poles and zeros with multiplicity. This is a subgroup of div C. We showed that. So div A is a subgroup, div 0 is a subgroup. In the future, we will show that div A is actually a subgroup of div 0. It's a tower. Yeah, then we define this LD sheaf, which is all those rational functions whose principal divisor is, whose divisor is at least minus d. So this is how we will quantify now. We will actually study approximation theorem in greater detail via this sheaf. I mean, this single definition will produce a large amount of theory, which is very important in the whole of maths. Yeah, so LD sheaf, remember, it collects, what it intends to do is it collects functions x, the functions x whose poles are not any worse than d or minus d. Okay, so the poles cannot have multiplicity worse than that in d, but it can be greater. So what first thing you should wonder is whether this, I mean, you can show that this LD sheaf is a vector space. That is easy. It's easy because of the valuation property. I think that's the, yeah, that's the proposition. LDS actually, let's recall what is LDS. LDS is similar to LD sheaf, but it's restricted to a subset of points. So all the rational functions whose poles are not any worse than S points in D. Okay, S are some points, so we are not looking at all the points in D, but only those points which are contained in the subset S. We'll generally take S to be finite subset. So divisor may have let's look at this distinction. So there are these two inequalities, x greater than or equal to minus d. D is a finite sum of points, but this inequality is making a statement about infinitely many points, because you are interested in x whose zeros and poles, although they will be finite, greater than or equal to minus d means that it is not allowed to have any pole outside of D, and it is allowed to have as many zeros as it wants. They can be from anywhere, but the poles are restricted by what you see in D. Actually, it is not completely true. D may have both positive and negative order points. So for positive, it puts a constraint on the poles of x, and for negative order in D, it puts a constraint on the zeros of x. But it's a statement about all the zeros and poles of x, while this second statement is not. This is not a statement about everything. So this is a statement only for points in S. How do they behave? It is not a statement about points which are outside S. On that it is silent. So it's not immediately, you may not immediately read it that way, but it's actually what is meant. Because this, when you write x on the left, look at the definition of ds. So you are only looking at zeros and poles which are contained in S, and you are comparing them only for those you are looking at minus d. So only about zeros and poles in S. So that's an important distinction. Outside S, x may have zeros and poles. That is, they are free. There is no constraint on them. So then clearly LDS can be bigger than LD. LD is contained in LDS because LDS puts lesser constraints, so there will be more functions. And we have this property that LDS is a K vector space. This is true also for LD, and you have these comparisons. If you pick a bigger divisor, then the LD sheaf is bigger. If you pick a bigger subset, then the LD sheaf can reduce, and so these things actually follow from valuation. Okay, so now let us come to this theorem that we had started, which is a highly non-trivial quantitative statement about the LD sheaf. So what this says is that if you pick a bigger divisor, then as you know, LD sheaf gets bigger, and the amount by which it gets bigger is exactly given by difference of degree. Okay, and the way we will prove it, this we already discussed. We will basically look at the difference of ds prime and ds. So it's a sum of qi's. Qi's are points on the curve. It is so because we have assumed ds prime minus ds is non-negative. So every point in the difference divisor has order non-negative. So we can write them as qi. Qi may be repeated. They may not be distinct. And then if you look at this tower, how is D growing to D prime one point at a time. These are all this is a chain of subspaces. So you can actually count the dimension step by step. So the dimension of LD prime over LD is sum of the middle quotients, their dimension. And what we will show is the base case that for the middle quotient, the degree is just of a single point, dqi. Okay, and then you will get the result. So let's look at this base case. When you add a single point, we want to show that the dimension of the quotient is just the degree of q. In particular, if your q refers to only, it's a cloud of points where there is only one point, then the degree is just 1. So LD plus Q grows by only one dimension, exactly 1. Okay, it's an exact result that we'll now prove. So how will we prove it? It's unsurprisingly, we will actually look at the this neighborhood around Q, right? Because Q is the new thing, so we want to understand what happens when you add Q to the divisor D. So you look in the neighborhood of Q, which means you are looking at the germs, which is this I guess RQ. So you are looking at this ring RQ, the germs around Q, and you mod it out by the maximal ideal, which are the germs that vanish at Q. So that gives you the residue field. Now this residue field, since we are in the general field case, this residue field may be slightly bigger than K, small k. So there will be a basis. It's a field extension of small k. So it's a vector space over small k, so you look at a basis of this.
So what's that set S again? Can you repeat? Taken as set to be Q P to Pn.
Oh yeah, sorry. This S is just in the claim. S is just a finite subset of points.
Okay, so this contains Q.
Yeah, and it has to contain Q because that was in the theorem. In the theorem, well, the way we are looking at this ds prime minus ds, these QIs that we are looking at, right? These are all in S. So Q1, Q2, everything is in S. So in the claim, the point Q that has been added, that is in S, so we call that P1. And then there are some other points which are unrelated. They may be n of them, n minus 1 more points. And degree of Q happens to be D. Let's assume that, denote that. Okay, so right, so let that basis be so this degree by definition is actually the degree of this field extension. So you get D many. So let x1 prime to xd prime be the K basis of KQ, the residue field, when seen modulo MQ, because RQ is just the ring that's just the DVR or germs. The field you get only when you mod out by MQ, maximal ideal. So x1 prime to xd prime modulo MQ, they give you a basis. Okay, we start with that. D is the degree of the point. So all action is now happening in the germs around this Q, and we'll try to understand L of D plus Q. So here we invoke the approximation theorem. Yeah, so some things here will be tricky. Hopefully you will understand better once I have given the proof. But remember that this x1 prime to xd prime that I have, these are the functions, right? Now we don't yet know whether they actually live in LD plus Q. So we'll actually identify elements inside LD plus Q. So for that we have to work a bit. So let's start that work. So we'll get it from approximation theorem. So by the approximation theorem, we can find another k basis x1 dot dot xd, more functions, such that so what we want is xj and xj prime should be roughly the same. So by that I mean that the valuation should be at least 1, which means that xj and xj prime are the same mod mq, right? So it is just xj is just xj prime plus some maximal ideal element. So they are approximately the same. And for other points P, the valuation is at least non-negative. Yeah, so this is a simultaneous set of inequalities that you have to satisfy. It's given by the valuations of all the points in S. So with respect to this Q, distinguished point Q, xj, xj prime are the same, approximately the same, and for other points, the valuation is non-negative. Okay, this is simultaneous system can be solved by approximation theorem that we have seen 2 to 3 weeks ago. So this will give you x1 to xd. These are just the primes slightly modified. Is that clear? And also by the approximation theorem, we can find an element u in k star such that u is in u's order is d plus q. So this we are doing because we are interested in the L d plus q space. Okay, so we want this condition for all p. Yeah, so this in particular means that u is in L d plus q S. But it's actually a bit stronger because being in the L d plus q sheaf, you just want it greater than equal to 0, but here we have set it to 0. But this u also you can find by the approximation theorem. And the advantage of this u is that now you get any rational function in the L d plus q sheaf satisfies this condition. So this u actually helps you to map the functions which were in the sheaf of interest, this L d plus q, it maps them into RQ. Okay, this ring, which the ring of the DVR or the germs for which we have a basis found, this exactly is the connection between the LD plus Q sheaf and the ring. Why is that true? Just look at the order. So to show that it's in the ring RQ, you have to look at the valuation with respect to Q of XU inverse. And what is that? Valuation of X minus valuation of U, which is, so valuation of X is, because it's in LD plus Q, valuation will be at least minus D and minus 1, right? So minus of this, and the valuation of U is by definition this. So you get 0. It was designed to satisfy this condition. So valuation of Q, valuation of U and valuation of X are the same actually. Sorry, yeah, greater than equal. So valuation of X, you only have an inequality, lower bound. But for valuation of U, you have exact matching thing. So they cancel and you get 0. So which means that XU inverse valuation 0, so it's in the, actually since in the, it's a unit then.
No, it's greater than 0. Greater than equals to
Greater than equal to 0, sorry, yes, correct. So it's in the DVR. Right. So it is just a scaling function which allows you to connect now, to bring everything in LD plus Q sheaf to the ring of germs. And so now you can already imagine how the proof will work. We'll now try to show that the basis that we have found in RQ, it gives you a basis for LD plus Q. Right? So this basis here will become basis there, and that will be your proof of the claim. So for that, let us now use the xj primes to make it work. Okay, so this means what we have just shown in blue. This means that XU inverse has a unique expression in the basis up to the maximal ideal. So there is an x prime. So AJs are in the base field and x prime is in the maximal ideal. So you can write XU inverse mod M Q in the basis because it's an element in the ring and you have a basis found already, x1 to xd, and AJs are field elements. And you have something for about x. So right, so now we have to understand where are xju and x prime u. I want to show that they are in the LD sheaf. That would give you a basis in the LD sheaf. So let's check that. So where is x prime u, for example? So the valuation of x prime u is what? Now, what is the valuation of x prime? X prime is in the maximal ideal, right? So it's at least 1. And u is by construction this. Which is equal to minus order of d. Because order of q in q is 1, 1 minus 1 is 0, so you get minus order of qd, which means where is x prime u? It's in the LD sheaf. Sorry, not yet. We have to prove one more property for other points. So for points what happens for the other points? For q you have understood. For other points, Vp x prime u what is this? Yeah, so I guess we have to look at this equation now. The green equation, x equal to sigma plus x prime u. So from there, this will not actually help. We don't know those values, but the equation can still help. So valuation of x prime u has to be can I say at least x? I can, right? Right. For xj u, Yeah, if I can get to this, then I'll get. Then I'll get this. How do I do the middle step?
VP of x prime is greater than equals to 0, and what is VP of u?
VP of x prime.
Huh?
No, we have not said anything. That is the problem. I don't know VP of x prime.
xj is 0.
Yeah, it's only VP of xj that is at least 0. And VP of u I have exact control. So and VP of x yes, so I think I have missed this calculation. Something here is missing. So this part is coming from the fact that x is in L d plus q. So this is fine. Where is this part coming from? Should come from the equation because
No, from the second equation, x u inverse equals to summation of a xj.
yes, yes.
So if you apply valuation on both sides, you get this quantity has to be strictly positive. A summation of aj xj.
Valuation has to be greater than both, right? Minimum of both.
No, if you pick a term a1 x1, valuation of a1 x1 is valuation of a1 time plus valuation of x1. But a1 is a unit.
No, VP of x plus y is greater than VP of x.
No, valuation has to be at least the minimum.
The VP of x plus y is greater than VP of x. So VP of x prime u is VP of x minus summation that
Mm-hmm.
greater than VP of x.
Yes.
Get that.
No, but how do we know that the valuation of x is
The x prime u is x minus summation j aj xj u. That's
no,
VP.
that part is fine, but how do I compare the valuation of this with x?
It has to be greater than both, right?
No, it's not greater than both. It's from greater than the
Minimum.
at least the minimum. So I have to compare valuation of x with xju. Yeah, I don't think I can do it right now. Maybe Deeptujit will tell this afterwards. Let me move forward. So this will fill the detail. Because right now I can't immediately think about.
If you reduce this VPU equals to minus or order of p plus q, and plugging into that equation the ai xj times u. Now, since ai is a unit, they will be 0, and xju will be valuation of xj, which I know to be positive, and valuation of u. So valuation of u is greater than equals to valuation of.
See, what I know is, okay, let's do it. So valuation of x with respect to p, I only know from this LD plus Q sheaf, right? That it's at least that in D. And what do I know about valuation of xju? So valuation of xj is at least 0, and valuation of u is minus order D. Oh, I see, I see. Okay, the middle term is not needed. That's I'm making a stronger claim, which is not required. It is just this.
Okay.
Yeah, that was the mistake. Yeah, is it clear? So actually, valuation of x, valuation of xju, all these I can compute for for p. So vpx is at least order of d, and vpxju is at least also minus order of d. So then x prime u is forced to be at least that much by the equation. Okay, so now I know about whole of S. I know about Q, I know about all the P's. So I can now say that x prime u is in the LD sheaf. Is that clear? Yeah, so the zeros of this x prime u function is, they are not any worse than minus d. And so that is good. So the error term, kind of the error term coming from the maximal ideal, it actually maps into the LD sheaf, which anyways we wanted to do mod, right? So this is going in the correct direction. So what we have deduced is that the dimension of LD plus QS mod LDS over the base field cannot be more than that equation, right? That equation AJ XJU, you have identified this basis, you take any combination, all these x's get produced in the LD plus Q sheaf, modulo LD sheaf. So the dimension is at most D, right? That is what we have shown. So we have shown the upper bound. We want to make it equal now. So let's do that.
Once I repeat why it is less than d.
Oh, less than dy. Let's as so do it for all. Because of this, we actually went over all the x's in the LD plus Q sheaf. Every x actually is generated by the same xju, which are only d many. So the dimension is at most d. Now all we have to show is that these d elements, they are actually independent. They form a basis. So let's do that next. So assume that in case this y, some y aj xju becomes dependent, which is it's in LDS, then what can happen? So then we want to show a contradiction, right? If a combination of xjus they map to 0 mod LDS, it should be a contradiction. So what is the contradiction? So let's take out u. So sigma aj xj is equal to yu inverse and so which means that yu inverse modulo the maximal ideal xj and xj prime are similar. We'll now use that property. So this right, xj and xj prime were equal mod mq, so I get this and oh yeah, so xj prime was also a basis. Yes, so this x1 to xd was a basis mod mq, so is x1 prime to xd prime, that also is a basis. So this is in then the is non-zero in KQ. It's actually a unit in the residue field because we are looking mod MQ, so we are in the residue field. It's a unit. It's a unit. I mean, it's a non-zero field element.
How did this came? Summation aj xj is equal to aj xj prime. You know that VQ of xj and xj prime is greater than 1. Right?
Yeah. So that means that xj and xj prime are the same mod MQ. MQ has this uniformizer. You are saying that its valuation is at least 1. So xj minus xj prime is divisible by the uniformizer. So yu inverse is actually a non-zero element, and yeah, I'm not sure why this xi prime is needed for this. No, sorry. No, we started with some arbitrary xi prime. Then we made it better by using these x1s. Okay, sure. Yeah, this is fine. So what this tells you is that yu inverse is actually valuation is 0. It's a unit in the residue field, so the valuation is 0. So this means that valuation of y and valuation of u has to be equal. And that is a contradiction. Why is that a contradiction? Well, because valuation of u we know, it's minus order of q d plus q, right? And if you assume that y is in LDS, then y should have order at least minus d, but here it's lower. It's one lower, right? So which means that y is not in LDS. That's the contradiction. Okay, so this contradiction means that any combination of xju is non-zero modulo the LD sheaf. Fine. So this means that dimension of LD plus Q mod LD is greater than equal to D as well. That's all. Okay, that's the proof. So we have found a basis, and it is the full basis. So we have found the exact dimension. So this proves the claim base case, and from base case you can go to the main theorem. So we have proved the main theorem that dimension of LD prime mod LD is degree difference. 1 point at a time you can do this. Okay, any questions? Yeah, so this gives us a very powerful handle on the LD sheaf. I mean, now what we want to do is we want to remove the S. I mean, because we want to actually understand the LD sheaf, not the LDS sheaf. But that can be done easily. So let's do that. In the following corollary. So for any d prime greater than equal to d divisors, dimension of LD prime mod LD, remember that LD is the subspace of LD prime over the base field K. This is at most degree of D prime minus degree of D. Okay, so this is weaker because it's not an equality anymore. It's only an upper bound. While in the theorem we had an equality. So why is that why do we have this difference? The difference is because that S was actually a finite set. We took a finite S. So finite S allowed us in the proof to do induction. But then when you work with LD prime, or I mean LD prime without the S, without the restriction, the conditions are actually not for finitely many points but for infinitely many points. So we don't know how to handle that. So we don't get the exact equality, but let us anyways get something. So we'll use the theorem, right? So let's define S to be the support of D and D prime. Obviously D prime and D are divisors, so it's a finite sum of points. Take all these points that you see, that is S. And then what should you do? Then you should invoke the theorem on LDS and LD prime S. That will work. So let's just check that. So LD prime well, you know that LD prime is a subgroup of LD prime S. You also know that LD is a subgroup of LDS. And you know that LD is a subgroup of LD prime. You know these easy conditions of subgroup containment. So from this actually you can make sense of LD prime by LD. So LD prime mod LD can be seen as a subgroup of this. Okay, why is that? See, the only non-triviality here is that on the left hand side LD you are treating as 0. We are going mod LD, right? So this containment can only be achieved if LD is a subspace of LDS, because on the RHS LDS is considered 0. So when you consider LDS 0, you have to show that LD is subsumed in that, but that is obviously correct because you know that LD is a subspace of LDS. So can be seen as it's a injection. Okay, it's an injection. So is that clear? So nothing else other than LD is in the kernel. That is what you have to show here. Yeah, but because of these containments, I think you can complete this. This is almost obvious. And once you complete this, you get the upper bound by the theorem.
No, I'm not sure about the injection because if you take an element outside LD,
Yes.
you are considering that its class in LD prime, modulo LD.
Yes.
Now,
And then it's also an element in LD prime S. So you can go to the image.
yeah.
It's the same element.
And you have to take now modulo LDS.
Yes.
But LDS is a bigger space, so it can be 0 also. That element can map to 0.
Yeah. So that is why maybe it's not as trivial as I imagined. But still you can do this. It's just a comparison of subspaces. I mean, no other property of curve is used here. It is just these 4-5 subspaces that you have to study. Okay, let's try something. So LD prime mod LD is equal to do you agree with this? I think that is the key thing which will stop the problem that you were talking about.
No, if you go back to your previous statement, do you need an injection to?
Yeah, because I want an upper bound of dimension. If your map itself is killing half of your basis elements, then you cannot get the corollary statement, right?
Yeah, but its dimension will be strictly less than.
No. Why? Your map is already, I mean, you are already setting basis elements to 0. So then when you go to the image, its dimension doesn't upper bound because you use the wrong map. No, it has to be an injection. I think the problem that you were saying is resolved here. So this quotient vector space, you basically have to observe that it's the same as this, and yeah, which is isomorphic to mod LDS. Okay, these are just basic properties from subspaces. So this quotient space is isomorphic to this sum, which then is contained inside LD prime S mod LDS. This gives the injection. Okay. Yeah, that will be the formal sequence of steps you have to do. And then you just invoke the previous theorem. Okay, so this step, basically the last step is where the problem is. In the last step, it's only a containment. So this last quotient space may be actually bigger, which is exactly given by the theorem statement. The left hand side may be smaller. LD prime mod LD may be smaller. Okay, so we don't really know how much smaller it is. So that's corollary 1. You just get an upper bound.
We don't know if this is straight inequality also.
Right now we don't know, but later on as the course progresses you will see that in reality these are different. Yeah, but at this point probably you can construct examples. I don't have an example ready, but in reality it won't be an equality. Actually these questions that you are asking, these are interesting because this is what inspired Riemann to define genus. So as the genus of the curve will increase, this inequality will get worse. It will kind of fluctuate. Sometimes it will be equal, sometimes it will be not equal. It will really depend on the genus and the divisors D and D prime. So exactly measuring the fluctuation is the source of this algebraic definition of genus, which we will see tomorrow and later. Yeah, so with that motivation, let's define an important function, the L, this dimension of the LD sheaf. But when I write this, you should ask, why is this finite? Right? Because till now I have given you no reason to believe that LD sheaf is a finite vector space. It was just collection of rational functions which have poles no worse than D. So these could also be infinite. I mean, the dimension. Definitely the functions are infinitely many, but even the vector space can be infinite dimensional. Everything can be infinite. So corollary 2 says that actually this is finite. It's a finite dimensional vector space. So LD is finite for all D in the divisor. Okay, that is what is so impressive about the theorem. The theorem actually implies this, that LD is a finite dimensional vector space. So, do you see why? Yeah, we'll just go to the theorem setting, just compare D with some other divisor, and that divisor will be, so take a positive divisor, strictly positive. This exists because, remember, every divisor D is a sum of finitely many points. So whether you have finitely many integers, you just pick the minimum integer and use that negative number to define minus D0. Right? So D0 is a positive divisor such that none of the orders in D are worse than minus of that. Now, what can you say about L of D0, minus D0? What is this space? See, these are functions such that this is greater than or equal to D0 or 0. Right, that's the L minus L sheaf. See, D0 is positive, right? So, is there a rational function whose principal divisor has only positive, either, whatever there is, it's all positive. Can that happen? In particular, there is no pole. That can't happen, right? There is no such rational function which has no pole.
Yeah, but we didn't see the proof of that.
No. A rational function is G by H. Yes, H can be unit, but then you only have Gx bar. So Gx bar has a kind of pole at infinity. For example, look at x. Right? So this is x over 1. You see it seems that there is no actual pole, but still in the projective space there is this pole at infinity. You see it by homogenization. You introduce z, so it's actually x by z, and z equal to 0 is the pole now. That's the point at infinity. So So yeah, so this actually then has to be a constant, but then if you take a constant, it also has no zero. So a constant has neither zeros nor poles, but we have said that d0 is actually positive, right? So it has to have a zero but no pole. So nothing is possible here. There does not exist an x as d0 is positive. As we need zeros but no poles. So the only option left is zero. So that's all. That's L minus d0. Okay, so L minus d0 is actually 0. That's an easy property for L sheaf. We could have seen this as an example when we defined the L sheaf. Right, so now you, on this situation you apply the theorem. So you will get dimension, so basically LD is equal to dimension of L minus d0 is anyway 0, but in the theorem hypothesis we will use LD mod L minus d0 quotient space, which will be by corollary 1
That is finite. So we'll
degree of, no, exactly, we will get upper bound. So degree of d minus plus degree of d0. So that's finite. Is that clear? So that is the ultimately the beautiful machinery which tells you that the LD sheaf is finite for all curves and for all divisors. Okay, so yes, any questions? So corollary 1 is telling you that LD prime minus LD is less than or equal to degree of D prime minus degree of D, right? That's how we'll read it. So that's exactly corollary 1. So what this is saying is that if you make your divisor bigger, then the L dimension is better approximated. Sorry, have I made a mistake? Yeah, that's a mistake. It's less than or equal to. Yeah, it was an upper bound, so you get this LD prime is upper bounded by LD. Yeah, so you should read this as following. As the following this, as you increase your divisor, the difference gets smaller. In other words, L is better approximated by the degree. So as D prime increases, LD prime gets closer to the degree, it's a better approximation. Or at least this is saying that it's not any worse. So working with bigger divisors will be helpful in the analysis. You can just understand it like this. So the question here is, in the limit, will L become equal to D? So do large enough D satisfy LD equal to DD? Right. So if you take a very big divisor, then in terms of degree, I mean, will the L space be exactly equal to the degree? If not, how much is the difference? Is this difference going all the way to minus infinity and so on? Right. So these are the questions. Because it could keep on decreasing. So if it decreases, will it reach minus infinity, or will it reach 0, or will it be positive, and so on? So we will now be interested in understanding this difference. And so answers to these questions will lead to genus. Genus of a curve. Okay, so the new term genus, which is an important invariant of a curve, that appears because of these issues, or you want to understand these issues. And actually a lot more analytic algebraic structure will come because of our attempt to understand this difference. The thing is that degree is something which you easily understand in terms of points. It's basically just counting the points in your cloud of the prime ideal. But L is something more mysterious, because this is to do with the rational functions which satisfy certain number of zeros and poles. So that's a much more mysterious thing. It's more algebraic analytic, and the two things will actually come together to give you genus. So we will, I think, do that after the recess. Tomorrow what we will do is we'll work with degree of principal divisors. We'll prove some theorems about that. Okay, we'll try to understand these principal divisors. Sorry, not 0a. We'll try to understand what kind of zeros and poles and how many do they appear in rational functions.